Hello, I'm Ondrej, and I'm excited to learn more about our paper called Feed-Forward Latent Domain Adaptation. This is a joint work with Dash, Shell, and team. Our goal is to adapt the model on a user's device to optimize performance on the local data distribution. More specifically, we deploy a pre-trained model to many edge devices and then use devices' own data to quickly adapt the model for the current test image. There are several challenges and data associated with this setup. First, we want to keep data local for privacy, which means we have to rely on local processing without using the cloud. Second, we like to have a purely feed-forward solution because back-propagation is slow and may not be supported on mobile devices. Third, there are latent domains and data because users' local stored data is of mixed relevance to each test instance. Fourth, there are no labels for users' examples. More specifically, there are no class or domain labels, as any sort of annotation will be inconvenient. However, we assume the same label space for all images. Finally, consider source-free setup where we have access only to the pre-trained model and not to the source data. This is because the source data can be private, but also because it can be hard to store on the device. Identification of this new practical setup is one of the key contributions of our paper. One of the key aspects of our setup is the presence of latent domains. As part of latent domain adaptation, we try to identify which images are relevant and use them for adaptation. Note that as the examples show, human annotation in terms of domains may not be optimal and more relevant images can come from other domains. For example, images from camera 1 and 3 are more relevant than from camera 2 simply because they were taken during the day, similarly as our test image. In contrast, in standard domain adaptation, we assume all images come from the suitable domain. Images on the user's device are likely to come from various places that represent various domains, and so a latent domain adaptation model set this setup well. In our setup, we can model users as tasks. Each user has their own set of unlabeled images, also known as a support set. We model this using images from randomly sampled combination domains, which are used for adaptation of the model. For benchmarking, we have labeled the images for each user, known as the query set. These come from one of the domains available in the support set. Now that we know more about our setup, we can present our solution. We propose a method called CXDA, which uses the cross-attention mechanism to identify and exploit relevant support instances for adapting the model to the query example. We pass the support image and the query image through the feature extractor, and then use the cross-attention module for identifying which support images are relevant for adaptation. We combine the query image features and the transform support set using a connection before making a prediction using the classifier. We use image-to-image cross-attention where we flatten all features of an image into a vector and use it for reasoning about what images are helpful for adaptation. The overall workflow is that we do pre-training across many randomly sampled tasks. For each task, we have two steps, inner and outer loop. In the inner loop, we do feed-forward adaptation using the support set. In the outer loop, we do gradient-based training of the model parameters, including the cross-attention mechanism. The inner loop uses unlabeled data, but the outer loop looks into using class labels. After pre-training is finished, we can deploy the model to many edge devices, with each represented by images sampled from new previously unseen domains. For this, we simply do feed-forward adaptation or use the cross-attention mechanism to condition on the support set. We evaluate our method using several synthetic and real-world benchmarks. These include Feminist, CFRC, dynamically, and iWildCam. We compare our approach with various feed-forward baselines, back-propagation-based functioning methods, as well as more advanced baselines and modifications of existing methods for open component adaptation, continual adaptation, or latent domain adaptation. We see that our CXDA clearly outperforms all the other approaches, both in terms of average task performance, but also in terms of the most challenging 10% of the tasks. As part of the paper, we also study various other questions, including the impact of domain-supervised adaptation. The results show that domain supervision is helpful in multiple cases, but can be outperformed using automated techniques. This suggests that human annotation may not always be optimal for adaptation. Our key focus is on efficiency, so we show that our CXD is capable of real-time adaptation with similar speed as the other feed-forward baselines. It is significantly faster than the back-propagation-based approaches and overall obtains the best performance thanks to its mechanism for identifying which exemplars are suitable for adaptation. We have analyzed the attention weights across many outcome tasks to better understand how CXDA works. We see a significant weight is spent on attending to examples in different domains. This suggests that CXDA exploits knowledge transfer beyond the boundaries of standard domain annotation. However, there is overall more attention to the in-domain instances, which means CXDA has learned to match query instances with corresponding domain instances in the support set. We also show what the attention weights look like on an example task. We can see that most weight is given to similar looking images from the same domain. Images that look very different receive less weight, while images from other domains that have some relevance also receive a certain amount of weight. To summarize, we have introduced a new highly practical problem setting for resource-constrained devices. It is characterized by unlabeled data that come from a mixture of domains with the need for feed-forward adaptation. To address this practical problem setting, we have developed a novel solution based on cross-attention that selects relevant examples and uses them for real-time adaptation. Thank you very much, and we look forward to seeing you at the poster session.